Okay, so we're lesson 11.7, surface area and volume of cones. You need to look at page number 641 and read through that page and look at the diagrams before you watch the rest of this video. So hit pause, look at page 641, take a look at that for 5 or 10 minutes, and then play this and we'll talk about the rest of it. Okay, I'm assuming you did that. So we're going to talk about the surface area of a right cone. So a right cone, this is a circular cone, looks something like this. I suppose I should have made this back part dotted because we can't see all that, can we? All right, that's beautiful. This formula says the surface area of a right cone is pi r squared plus pi r L. And I'm not sure if you guys know what the L is. Now you should if you just looked at page 641 for a minute, but that's what we call the slant height. And that is the distance from our vertex here down to this point right there. So there's our slant height, and then our radius right there. Okay, and all we got to do is plug the parts in and work it out. So if our radius is 5 and our slant height is 12, okay, we can work this out. Pi times 5 squared plus pi times the radius times the slant height, and we end up with 25 times pi. That's the correct way to write it. We're using pi like it's a variable, so we want to write it second. Okay, now up here, r is truly a variable, so pi comes first because it's a number that we actually know what it is. It's not actually a variable. Here, though, we know what 25 is, and pi is a symbol we're using like a variable, so it does actually come second. So plus 5 times 12, that's 60 times pi. And then look how they're like terms. Okay, that's going to happen each time, so we end up with 85 times pi. And whatever units we're in, remember we're going to have square units because we're talking about surface area. Now this is a right cone. I want you to notice this vertex point is directly above the center of the circle. If it's not a right cone, finding the surface area is going to be a little more of a thing. Okay, so we're not going to talk about that for now. All you got to do is, plug it in the formula. You're good to go. Now the volume of a cone, if you just looked at page 641, you see how the volume of a cone is 1/3 the volume of the circular cylinder that it fits into. So if I draw a circular cylinder here, okay, if we have a cone inside of it, now I hope you can imagine what I'm drawing. This happens to be a right cone, so this vertex would be directly above the center of our circle down here. That cone takes up 1/3 the volume of the circular cylinder. And this doesn't have to be a right cone. The vertex point can be over here, and you can have the cone looking like this, or the vertex point can actually be on the circle like that, and the cone can kind of come over here like this. It doesn't matter. In each case, the area of the cone, the base of the cone, is the circle, which is the area of the circular cylinder, and each of these has the same height as well. Now that one maybe it looks a little bit higher, but remember it's still on the circle up here that's parallel to the circle down here, so still parallel, still the same height. So the formula for the volume of a cone, at first they just give it to you this way: 1/3 capital B times H. Okay, that might be a little confusing. So capital B is the area of the base. So this works whether the base, maybe the base is a square. You have this cone that kind of looks like this. That's not the greatest cone ever, but it doesn't matter what the shape of the base is. The cone, the volume of the cone, is going to be the same thing, the area of the base times the height. Now for a circular cone, we can do it this way: 1/3 pi r squared. Now pi r squared, that's going to be the area of our circle on the bottom, right, times the height of the figure. So finding the volume isn't going to be any kind of big deal. If they give you the height of the cone, like on example number 2, they give you this cone, looks something like this. It's not a right cone. They do tell you the height is 4.5 centimeters. They do tell you the radius is 2.2 centimeters. Okay. Now, since this has already given us decimal numbers like this, then you're probably going to be expected to get out a calculator and work this out. So as you fill out the problem, you have pi times the radius squared times the height. This is a case where you're just going to get out a calculator and you're going to give an approximate answer. You're not going to try to give the exact answer necessarily. You can. It's not a big deal to get out the calculator and say, well, let's see, 2.2 squared times 4.5, and then multiply that by 1/3. That comes out to be 7.26 times pi. I guess this would be the exact answer still. Okay. But if they're giving you decimal answers here, they're expecting a decimal answer back. So we're going to go ahead and multiply by 3.14. That's close enough for pi for this one. And I'm looking at the instructions. It doesn't really say, so I'm probably going to round this off to 2 decimals, 22.80. Okay, so there it is. Now I notice in the book it says 22.81, and I put 22.80. I don't know if you guys noticed that looking in the book. Here's the reason though. I actually typed in the fraction 1/3 into my calculator. They've used 0.33 for 1/3, which isn't exactly the same thing. So we're getting a little bit of a rounding error, which is really common. So even getting to this point where we're saying that's the exact answer, if someone is using 0.33, so they're rounding this off to 0.33 when it's actually repeating, okay, and someone else is using 1/3 in the calculator and it's using 0.33 out to 9 decimals, so it's not rounding it off till it runs out of space on the calculator to 9 decimals. You're going to get a little bit different answer right there. So even that's going to be a little bit different and not the exact answer again. And that's just the nature of rounding and the problem that we run into. Okay, so the next part on example 3, finding the volume of a similar solid. It gives us 2 cones. One has a base where the radius is 3. And one has a base where its radius is 9. Doesn't really say much about the heights of them or anything like that, but it does give us the volume here is 15 pi cubic feet, and then we want to think about the volume over here if they're similar. Now remember, if they're similar, we can see the scale factor of the radius is 3, can't we? So that should give you a good idea of what's happening to the heights as well. Okay, if this one's 4, we probably have 12 right here, don't we? And do you think the volume is going to change in that same scale factor? Is the volume here going to be just 3 times greater than the volume here. And I hope you know by now that that's not going to be the case. Is it going to be 3 squared? Is it going to be 3 cubed times bigger? Think about that as you look at example number 3. Okay, good luck on this section. Don't be afraid to email me with questions on the assignment today if you have some questions, and then I will make a video answering whatever you need. Okay, thank you.